Welcome to the fourth video from this software engineering series. It talks about multilateral thinking, or in other words, thinking out of the box. You will see the power of hybrid algorithms in action. Every software program revolves around a collection of algorithms that lay out its flow of execution at different levels of abstraction. These core algorithms shape the overall runtime and memory characteristics of an executable code. Therefore, it's imperative to be to some extent knowledgeable regarding algorithm design, although you will indirectly reuse efficient algorithms simply by relying on standard and/or mature external libraries and frameworks. In this video, you will learn about one powerful algorithm design technique that combines many subordinate variants into a unified whole. This is the basis of all hybrid approaches. For example, most recommender systems are implemented in this fashion. Even if you just want to reuse already available algorithms, you might want to combine them in the spirit of hybrid systems. The table of contents is as follows. First, we will describe our use case to have something to work with. Next, we will showcase the implementation of our problem from the previous step. Then we will introduce the structure of a hybrid algorithm. And finally, we will show the main difference between hybrid and n-version programming methods. Here is the problem description. We will solve the following problem using Python 3. Chiode, which on Serbian means pins. This problem is freely available on the site called Petlja. Petlja is a Serbian site dedicated to promote computer science mostly for middle and high school students. It also hosts a platform to run competitions. The site offers valuable content in English too. The link from this presentation is going to redirect you to the English version of this site. Here is the problem description in Serbian, and I will translate it now to English. The first paragraph says that small z is seriously preparing for the next round of programming competitions. Since Z's class is well known by good programmers, Professor Dule has huge issues to stick the results from past online competitions onto the billboard. This billboard is a big cylindrical column inside the main hall of the school. The second paragraph says that the billboard's perimeter is long enough to attach exactly k square-shaped papers with results. You can neglect the overlapping area between papers to stick them through with pins. I mean, you have one paper, and when you overlap it with another one, these two pins can be shared. And this area here can be ignored. The billboard's height is effectively infinite. Dule is constantly struggling with pins. Help him to make a plan how to arrange all the results so that you can attach them with the minimal number of pins, and also taking into account the fact that each paper must be attached with 4 pins. Once again, you can reuse pins if you overlap the papers. One pin may encompass 1, 2, 3, or 4 papers. This section here describes the input. Inside a single row of the standard input, you have two numbers n and k separated with space. N is the number of competitions whose results professor must announce. And there is a one-to-one mapping between the number of competitions and number of papers, because the results of one competition must be put on one paper. Effectively, this means n may be regarded as the number of papers needed. K is the number of papers that may be arranged in a single row if you wrap it around. In other words, if you close full circle. This section describes the output. The output is a single number, the minimal number of pins. Let's look at this example. N equals 6 and K equals 10. If we arrange the papers in 2 rows and 3 columns, then we would need 12 pins. Notice that this way of drawing is much easier than drawing in this fashion. So I'm going to showcase this only once here. So these two are semantically equivalent. With these overlapping sections, and you can ignore these areas here. Okay, let's look at another example. Nine and 3. Here we can arrange the papers into 3 rows and 3 columns, and these are the pins needed. Again, we need 12 pins. Notice that we don't need, and let me mark it as green. So we don't need these because this is the 3rd column, and these papers, in other words, this edge here, is going to be wrapped around this one. So that this pin will hold this corner and this one, this, and so forth. This is the constraints section. We have time limit of 1 second and memory limit of 16 megabytes. Here is the result of unfolding the cylinder into a 2D grid. We will use this as a playground to try out different strategies and see what works and what doesn't work. Data scientists use a similar approach, and they call it an exploratory data analysis phase. The worst strategy is to put papers separately without touching each other. In this case, we would need 4 pins per paper, and in total we would need 4 times n pins. This number is clearly the maximum number of pins we need for n papers. By stitching papers together, we can lower the number of pins by sharing them. This allows us to formulate the following theorem. No separated areas are in an optimal solution. By separated areas, I mean 2 areas that don't share an edge. In other words, don't share a pin. We will prove this by contradiction. Suppose a contrary, that we do have in an optimal solution 2 separated areas, one having x number of pins and the other one having y number of pins. But now, by just moving these 2 areas closer and closer to each other until they collide, even if it happens in this corner like here, we can reduce the number of pins. And if we just manage to put one paper on top of other and only in the corner, we would already be able to reduce the number of pins by at least 1. But this is also less than our initial assumption, which means this is a contradiction. This ends our proof. Apparently, any optimal solution would try to pack papers as tightly as possible. But we don't know what is that strategy yet. This is an example with 23 papers and k equals 7, which means that this 7th column is the one wrapped around. These corners here don't require a pin. these are those shared pins for these guys on this side. Due to this wraparound effect, it's obvious that if you decide to put papers side by side, it makes sense to put them on a row by row basis instead of column by column basis. By the way, a column is anyhow treated effectively as infinite, so by laying out papers by row, we would eventually reach this final column that is wrapped around, and we can save pins here. This arrangement, or this strategy where we would just simply put papers row by row greedily until we hit the end and then continue on the next row, is what we are going to call a full row strategy. And for this full row strategy, we would need 31 pins for this example with 23 papers and k equals 7. We might think that we have just found a winning strategy. Let's try another example with k equals 9. Here is the arrangement for k equals 9. This row here is not fully filled and has 6 pins, and these require 9 each, so we have 3 times 9 plus 6, it's 33. After these two examples, let's do some analysis. What is really going on here? For the sake of simplicity, I will fix k on this fourth column and treat n to be infinite. What happens in the full row strategy is that this first column is the most expensive to be filled in. As you can see, we must start with 4 pins, and for each additional paper we will need 2 pins. Once we reach this fourth column, this paper, denoted with dashed line, is free to be attached because these corners are wrapped around. The first row is quite expensive because we need to start with 4 pins, and for each additional paper we would need 2 pins until we reach this final column. But what's going on in the next row is quite different. This first paper in this first column needs just 2 additional pins. Recall that these are already counted in and shared, and each additional paper will only require 1 additional pin. And this one is again free. So for this additional row and for this one and this one, if we continue up, the ratio between the number of pins and the number of papers attached per row, so papers per row, is equal to 1. And using 1 pin per paper for conquering new space is optimal. You cannot do better. To avoid ambiguities, I need to define what do I mean by conquering a space. On this left side, all this is a collection of papers that have been stick together and comprising this area. This outer edge is what I mean by the division line between inner space and outer space. Everything here is an outer space, and everything inside is an inner space. So if you have some gap here or some unfilled part of the space, any paper attached in this inside area doesn't count as conquering a space. On this right side, I am illustrating this with this 3 by 3 arrangement of papers, and suppose that now you are trying to put an additional paper into this space. You can do it freely by just putting it here and reusing all these pins, so it would mean that you can attach a paper here with 0 additional pins. But according to our definition, this is not counting as conquering a space. So conquering a space would mean that we extend this outer border in some fashion. Are we done? Can we do better? Let's see another example. In this case, k is very large, 100. Definitely by greedily trying to fill in the first row, we wouldn't succeed because we don't have enough papers. For this case, we would need 48 pins. Why? Because the first paper, and let me clear all this. So the first paper would require 4 pins, and each additional one would require 2 of them. So we would have 4 plus 2 times 22, and this equals to 48. This number here is suspicious. In a sense, it's suspiciously high. Let's try another arrangement. Instead of greedily trying to fill in each row, let's try to pack papers as much as possible by first starting to fill in full squares and then the rest of the papers to attach on the sides of that full square. For n equals 23, a full square would be 4 by 4. This is 16. And we would have plus 7 papers, these guys here. The total number of pins required in this case is only 34. Clearly 34 is much less than 48. Let's compare our two strategies on our previous examples. Our new strategy is called squared strategy, and clearly it packs papers together as much as possible, although in a different fashion. For this case, the square strategy is a winner. But for these cases, the full row strategy is a winner. Now, one might jump to a conclusion, there is a simple rule. If the number of papers is less than the k, then we would use a square strategy, otherwise we should use a full row strategy. Hastily jumping to such a conclusion would be a mistake. You must prove this rule. This cannot be done by tests, because tests are only good for discovering bugs. If your base assumption is wrong, you are just going to test that you have correctly implemented the wrong idea. There are two ways to prove this rule, what we have mentioned. Either to really try to provide a proof that it's all working in all cases, or you can provide a counterexample that will show that the rule is not true. In our case, it's enough to follow this second option and try out this example with n equals 23 and k equals 11. The full row strategy would require 35 papers. Our square strategy would still require only 34. Clearly, we don't have an absolute winner here. The crucial question is when to apply the full row strategy and when to apply the square strategy. Obviously, this rule is not as simple as we have thought. But how complex is this rule? And should we even bother? Another question is, are there any additional strategies? A third one. By the way, for this square strategy, we can show that the limit when n tends to infinity, where n is the number of papers, the number of pins as a function of n over n is 1. And we have already shown that this 1 is an optimal number of pins for conquering new space. This function pins for this square strategy is not depending on k, because we don't care about k. What happens if the k is very small. In that case, our squared strategy, suppose that this is the kth column, is simply going to overshoot or overestimate the number of pins. In that case, clearly the full row strategy will win. Here is the structure of a hybrid algorithm. It is consisted from different variants or strategies if you prefer. All of these solve the same problem and provide the results to a combiner. The benefits of structuring your algorithm in this fashion is exactly that you don't need to worry when to use variant 1 and when to use variant 2 or 3 and so on. As we have seen, this is not an easy question at all. The combiner would collect all the results and decide which one to choose as an optimal one. Usually these variants are executed in parallel. For a hybrid algorithm to be a good option, all of these variants should execute fast and should not be resource hungry. This structure is reminiscent of something called n-version programming. But there the goal is completely different. In n-version programming, you are sharing the same specification with multiple independent teams who develop their own variant. The objective is to eliminate fault. In other words, to build a fault-tolerant system. The assumption is that independent teams will not make the same mistake. Hence, one of the variants will always compensate the error present in the other one. Finally, here is the implementation of our hybrid algorithm in Python. This function is responsible for implementing the full row strategy, and this one for the other one. Both receive the same input. Data is holding the input and provided here for both functions. The results are collected and combined with this min function. This is a combiner essentially. The beauty of a hybrid algorithm is that this combiner can be trivial. In our case, min. So we don't need to worry about when to use a full row strategy, when to use a squared one, what are all those complex rules that we need to know in order to make a unified algorithm. What can we conclude from this video? Optimization problems can be often solved in terms of simpler suboptimal solutions. And this is the essence of hybrid-based algorithms, where multiple variants are simply executed in parallel, results collected, and then combined in a meaningful fashion. The hybrid method should be part of your algorithm design toolbox. A multilateral thinking skill is equally important as deep technical knowledge. Thank you very much for watching this video. I hope that you have liked the content. If that's the case, please subscribe to this channel, Composite Decomposition. Subscription on YouTube is free, and by being subscribed you won't miss any future episodes. Thank you very much.